Okay, so we're going to factor. Now, factoring is going to get more and more difficult. Guys, I'm this close to giving a sitting plan for 22 of you. Okay, like we should be able to get through the lesson without having to stop. 22, I think. Okay. So factoring is going to be a lot more difficult when you have a higher degree function. Did you guys factor like cubics and quartics, Tyler?
Yes, we did.
Yeah? When you learned the factor theorem? Awesome. So that you're going to have to do that. For degree 2, you can use the whole good old quadratic formula.
I can do that without a graphic calculator.
Yeah, you can. Once you
Yeah, the program only exists on the graphic calculator.
Okay, so quadratic formula. Now, if the above meant if it's not factorable and it's not degree 2, that's where you have to use Newton's method. And that's where I want to talk about that. I am not going to test you on this.
But it's something cool that we learned.
But I'm going to show it to you later on in this lesson. Yes, it's very helpful if you don't have a graphic calculator and you want to find the x-intercept and you can't factor it. And it's a higher degree than 2. Then you use Newton's method. Okay? If it's not factorable. So not factorable, synthetic division won't work.
What about long division?
Okay, same thing. It's really the same thing. Okay, that's where we're going to use Newton's method. It is a form of division, because, yeah, it is a form of division, basically, that's developed from. Okay, so we'll skip this for now, and I want to come back to Newton's method. It's pretty cool, actually. But all it is this formula, and I have to explain the formula to you. Okay, and that's how we can find zeros without a graphing calculator for a high degree. Okay, so what's the first derivative test? What does that tell me? Okay, it's our first derivative, and what does that tell you? The slope. So it tells us when our slope is 0, so a local min or max, or when it's rising or falling, so increase or decrease. So we want to set our first derivative to 0 and place the critical values on a number line. And obtain, okay, that, or you have to do that giant chart.
There's got to be a better way. I'm going to think of a better way.
Okay, so this shows clearly where you have your increase or decrease. You can see where you have the local max and min. And then we're going to identify the absolute local max and min. The absolute or local max or min. So you're going to have to show this. So we're going to start sketching graphs today, and we're going to add more steps each day as we go on. Okay?
So that's
Yep, it's going to be a lot of steps. If you look at basically 5.5, it goes through a lot of those steps. First page of 5.5. Okay? Because okay, exactly. All right, then you're going to sketch the curve. So place all intercepts and turning points. Okay. So when you plot it, you have to put all those critical points on the graph. So you're going to have to figure out the y values for those critical values and plot them properly. Okay? So let's go through an example for sketching this function. Okay? So the first thing we want to determine is its degree, because that's going to tell us the nature. Degree is 2, so we expect a parabola. Okay? We need our intercepts. So let's start with which one do you want to do first? Y is easiest. Okay, what's the y-intercept? If we set x to 0, it's negative 4. X-intercept, how are we going to get that? And how did you get that? Or you didn't factor? Okay, so factoring it, we get our critical value, our x equals 4 and negative 1. Okay, so we'll start by plotting those points. So we have 4 and -1 for zeros, and a y-intercept of -4. Now this is what's cool about this. Oh, isn't enough? It'll be good. Yeah, we'll be good. Okay, now we want to do our first derivative test. So we're only doing 2 out of 10 things at this point. Yeah. Do you have enough space there? Yeah, usually if you look at your assignment, one question's full page of work room. Okay, what is that going to tell us? Max and min and where we're increasing and decreasing. Okay, so y prime equals where our max is. You could probably guess, but we want to do everything accurately. Oh, you know what? We need to change our scale. Okay, I'll show you in a second. No, we can't. -2, oops. -2, thank you. -4, -6. We have to, yeah, sorry guys. I hope you use your pencil. Yeah, and that could stay the same. -1, -2. Those don't have to change. Okay, so derivative 2x minus 3. So what's our critical value here? So when we say 3 over 2. Okay, and what's that going to tell us then? 2 things. Put that on a number line where it turns. So if we plug in 0, because that's left of 1.5, it would be a negative. And then right of 0 would be a positive. So this function we could say is increasing from 3 over 2 to infinity, decreasing -infinity to 3 over 2. So as we build upon this, you're going to show all this work. Okay, now we want to check. So this, if we're going from a decrease to an increase, this is going to be a minimum. Yeah, in this case, it's an absolute min. So our minimum at. Yeah, wouldn't it have been way easier in grade 11 for quadratics? I don't know. For finding your vertex? Yeah, way easier. Okay, so min at, we have to plug 3 over 2 where? In the original. Awesome. I'm going to do this up here. 3 over 2 squared minus 3 times 3 over 2 minus 4. So 9 over 4 minus, so this is 9 over 2, so 18 over 4 minus 16 over 4. Trying to get a common denominator. We're with, no?
Yep.
Okay. Okay, so 9 minus 18, -9 minus 16, -25 over 4. So that's where, okay, so now let's finish plotting. We need to plot our -20. What is -25 over 4 equal to? 6.25, -6.25. And that's at 3 over 2. So like right there. So now we can sketch our function. You could even also use symmetry. The symmetry, you know about this function? No? Okay, well I knew this point here, our y-intercept's -4 is right here. So, and that was at 1.5. Oh, that, so there's, sorry. Plus another 1.5 would be 3. Right? Symmetrical there. Yeah. Yeah. Okay. Okay, so let's try another guy. Oh, yes. You guys are going to have fun with this one. Let's see how well you can factor trinomials. Or, sorry, third degree. Okay, let's start with the easiest. So intercepts, the y-intercept. Negative 6. Okay, x-intercept. I want you to try and factor this puppy. Use synthetic or long division.
Is it not going to work? You can just tell us.
It's going to work.
It is going to work.
It's going to work. I promise. Okay, what you might want to do when you're solving for your zeros, what could you do to make this a lot easier? Divide both sides by -1. Yeah. No, it's not. There's nothing fake about it. Okay? Makes it a lot easier to factor. I want you to try and factor this. Find one factor. That's all I'm asking. Find one factor. Use your factor theorem. Yeah. What are your do you remember learning what are your possibles?
Yeah.
Plus or minus b over a.
Yeah.
Yeah? So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So over 1. Okay. Minus 2? Okay, so did you guys use synthetic?
Wait, we're not done.
Like the chart? So x, you said -2 gave you 0?
Yeah, but how do
2?
you get there?
2 does.
How do you get there?
Okay, you plug in. No. Graphing is like a bad word in calculus. Unless it's okay, so we look at the last number. Great. Woo. Okay. So we look at the last number, the constant, and we want possible factors are the factors of that number. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. It's actually b over a, but our a value is 1, so we're good. So we guess and test. We're going to plug in these values into original function until one of them gives us 0. Okay? A 1. Otherwise, we have to incorporate the fractions. Okay, so we plugged in positive 2, Adrian? Positive 2 gave you 0?
How did you figure that out so fast?
Well, so you grab your calculator. Okay, sorry guys. I'll go through it. No, that's not what I want. Open. Oh, really? It's the same thing, though. It's just time. That's all it is. It's time. Okay, so either function, you can, a lot of yours you can still store x. Yeah? It's just a lot of work, okay? So here, to make you feel better, on a unit exam, you're going to only have one of these graphing questions, like on your written response. Okay? Oops. Okay. Okay, and plus 6 gives me 0. Okay? Now, there's two ways to teach this, so I need your help because I'm not sure how Mr. Trimble showed you. Did you put the positive 2 or a negative 2 here?
Put the number after the negative. Positive.
So if you got 2, you plugged in 2, you put the 2 here? Okay, so then we write in the coefficients, right? So 1, -5, 3, and 6. Okay, and the first thing you want to do is bring down the 1. So we multiply, right? 2 times 1 gives you 2. And what are you doing with these two numbers? You're adding them. Yes, good. Yeah? Oh, I just divided both sides by -1 so I can get rid of that ugly negative. You don't have to. It'll work out the same. Okay? Okay, so add them -3. 2 times -3 is -6. Add them as -3, -6, and 0. Okay? So in factored form, what does this become? So the 2 becomes an x minus 2. Right? If 2 would give you 0, the factor would have been x minus 2. This would be x squared minus 3x minus 3. Alrighty. Next question. Can we factor this dude? Shucks. So now we have to use, because it's second degree, quadratic formula. Okay, so x equals negative b plus or minus the square root. Did you hear that song before?
That's the one that doesn't work.
Oh yeah, I sang it to you, didn't I? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a.
You can put anything.
Okay. Alright, so we got... I know. Okay, whatever. Mock me all you want. Okay, this is good because negative 4 times the negative 3 would give you it's positive. Positive 12. 9 plus 12. 21. 3 plus or minus root 21. It's positive. Okay. Okay, what are they? Yeah? Yes. Yeah.
How do you find
If there's a negative inside the square root, then there's no x-intercept other than the 2. Because it's a cubic, so cubics could right?
But how do you find that value?
So what happens is when you factor this part, it'll give you a negative in the square root. And like what it would. Are you saying? Like so here's. Okay, like are you talking about this guy? That's a local min. You're gonna find it out.
Oh.
Yeah.
Could we have done that last
Yeah. Okay. Okay. Moving on. It's gonna be so easy now, right? Calculus, so easy. Okay, 3.79. Oh. Thank you. 3.79 and negative 0.791. Thank you. I appreciate that. Okay. What? Okay. How is this better than a graphing calculator? It's not. It's more work. But have to be able. It's just not, right? Okay, so I'm going to tell you now we still have to do some other things. I hope you have room. Okay, so we need our minimums and maximums, increase and decrease. So first derivative. Shh, guys. Okay, first derivative. Should we skip the next question so you can just run into that one? Oh, yours is on the next one? Oh, nice. Okay, good. Okay, first derivative. Greg, what's the first derivative?
First derivative.
What is it equal to?
It's equal to.
I don't have it in front of me, so you're going to have to figure it out. Look at the equation.
This equation?
Yeah, find the first derivative.
Or are we doing with negative or without?
The negative still, the actual equation.
Negative 3x squared plus 10x squared plus 10x minus 3.
Okay. Awesome. Okay, so this guy's ugly because we're going to have to factor him too. What?
No.
Okay, so factor this guy. Guess what you have to use? It's complex trinomial. Two numbers that multiply to 9, add to 10. Negative 9, negative 1. Okay, so what do we do with our middle term? Break it up. Okay, so what can you factor out here? 3x, x minus 3, factor out 1, negative 1. And we get negative 3x minus 1, x minus 3. Okay, so we need to do an interval test. What's our critical values? 1/3 and 3. You with us?
I'm with you entirely.
Okay. Okay, now here's where you have to be very careful of your interval test. Why do you have to be careful? The negative on the outside counts. Okay, give me a number less than a third.
0.
0. Okay, so we have a negative. This when we're doing our interval test, figure out increase or decrease. So negative times 3 times 0 minus 1 would also give you a
Negative.
negative times 0 minus 3 would also give you a negative. 3 negatives?
Negative.
Negative. Okay, now cubics, be careful. Don't always, well, I guess the derivative was a quadratic, but got to test all of them, right? Because it could also do like, yeah. Okay, so now we still have the negative on the outside. A number between a third and 3.
1.2.
How about just 1?
Okay.
Okay, thank you for not being mad. 3 times 1 minus 1. Positive, thank you. Okay, 1 minus 3 is a negative. So a negative times a positive times a negative. Positive. Thank you. And above 3, like 4, so we have the negative on the outside. 4, this would be a positive. Oops. And then positive, so it would be negative. Okay, so now what does that tell us? No, it tells us something. Okay, increase, decrease first. Okay, so where is it increasing? 1/3 to 3. Where is it decreasing?
Everywhere else.
Okay, so negative infinity to 1/3, union 3 to infinity. So we have down, up, down. So which one's our local min? Or we'll just say, yeah, it's the local min. Okay, so f of 1/3. Guess what you have to do with that guy? Yeah, this is. Okay, do you want me to just tell you what it is?
Yep, pretty much.
Okay, so plugging it into the cubic, you are going to get negative 6.5. Okay? It doesn't seem so bad when you didn't have to plug it in yourself.
Yeah.
F of 3 is going to give you 3. Yay. So looking at this, obviously we need to change our scale. So we're going to go 2, 4, 6s on the y. That was, oh, thank you. Miss Johnson, local min, this is local max. There you go. Okay, so let's sketch this now. So first thing we want to plot is our intercepts. So do the best that we can. So we want to have one at 2. Where else?
1/3.
3.79. We're doing intercepts.
Oh.
Y-intercept is negative 6. Another intercept 3.79 and negative 0.791. Okay. Then our local max and mins. So we had one at 1/3 and negative 6.5. So like here, this was a min. And we have our max at 3 and 3. Okay, it's a negative cubic. So a negative cubic starts in which quadrant? Top left. So from 2 to bottom right, which is 4. Okay, let's sketch this. So we know this is going to be, this part's easy. Is that right? Decreasing after 3. Yep, good. Okay, and there. Let's just connect the dots. You know it's a cubic, so you know what it's going to look like. It's not so bad. Okay, how are y'all feeling? Did you want to try the next one all on your own now? Or what do you want to do with that guy? Leave it? Okay. So, you don't have the notes for Newton's method, do you? On the very end of the very end of this unit. So your homework is actually in the book.
It should be like that all the time.
Which is good for you. I have extra textbooks. I'm storing them there.
No, but it's just like
Okay. Yes, I did. So 3.6 is at the end of the unit. So Newton's method. So technically today's lesson is really nothing new,
it's the last one.
right?
The last one.
Yeah, I just threw it at the back because it's extra. Okay, so in university, if you do calculus next year, which I'm assuming most of you will be, that's why you're here, or you're using this as an option, so you don't have to use another course. So it's really the two situations.
Or you're just here for fun. Yeah.
Or you're here for fun. That happens too. Which, yeah, totally. Because you're going to have math withdraw otherwise. Okay? I promise you though, if your first year university, your first course, if you're just going into 114, it's like a repeat of everything we've done here. Yeah.
What if you go into 130?
Same thing.
Is it actually like the same?
So 113 is just for those who haven't taken calculus before and haven't taken math 13 or math 31. 114 are for those who have taken. So I believe 113 has a lab. If you've taken calculus in high school, you get to do 114, which has no lab. So it saves you lots of time. It's the same course, except for 113 are for those who don't have calculus like math 31 before. You do. You've taken it before. But you don't have to do a lab, which is nice. At least that's how it was in the last couple of years. Okay, so let's talk about Newton. Yeah. Both of them are mostly. There are some stuff that are different, and they go a little bit farther, but most of it's repeat, which is good.
But if you're from a curve and I suck.
When you have 5 courses your first semester, right? And they're all like intense. It's nice to have one you're like, I've seen this before. Okay. So Newton's method is an approximation method. I stepped on this, sorry. Okay, guys? So, many math-based problems reduce to solving. We want to solve f of x equals 0. It's impossible to factor, and it's not a quadratic. So this is where we can use Newton's method to approximate. So, let me walk you through this diagram. It kind of looks similar to what we've seen before, right? So to solve when our function is equal to 0, right, what value of x would make my function equal to 0, we need to find x-intercepts, or the roots. So what we do is we take a guess.
Like any guess.
Any guess. And usually you have like an idea, but any guess. Okay? So you make a guess. That's what your first guess. Greg? Guys. Okay, so then after that, we determine, okay, obviously this guess is probably not right, and we plug it into our function. So we get the point, our guess, and the y value for our guess. Good to go? Okay?
And then we realize we're not close.
So then we take, this is more the theory into getting actually the formula. If we draw a tangent line at this point, so here's my guess. So I was guessing here, but it's actually this point. And we draw a tangent line. What will happen with this tangent line is it will give a better guess than I did for a 0. So his 0 is better than my original 1. Then I plug him in and I draw his tangent line. this 0 is even better than the previous one. So then I plug in this value and get this tangent line. And the 0 for that tangent line is even better until we reach it. So it doesn't matter what your guess is, you'll sooner or later get to the actual value. Why? Because no matter what, it'll then give you the same number every time, so you know you have the 0. Okay? So if we draw a tangent line at this point, it will intersect the x-axis at x2 and 0, which will be closer to r than your original guess. On page 148, there's kind of more of an explanation, and you can look there later if you want to. Do we want to talk to about the lot? Is this about? No? Okay. We're good? Okay. Okay. Okay, sounds good. Okay, so I'm going to write in a few equations. I think, oh, it's all here. Don't worry about it. Yeah. Okay, so basically everything stems from this equation that you know. Landon, do you need to leave? Can you stop? It's rude. Come on. Do it, Landon. You keep doing that all class. It starts to get on your nerves.
Getting a little tiring.
Yeah, like the first time, haha, Landon.
Okay, so you guys remember, how many of you guys have seen Friends? Who watched the show?
Good old slope. We call that, what do we call slope now? At that point, right, for our tangent line, that would be f prime of x1. At that point, that tangent line that we're drawing. This guy here. So his slope of this tangent line is f prime of x1. So good? So we plug that into our formula. We have x2 minus x1. We know y2 equals 0, right? We're plugging in these 2 points, and that's how this formula was developed. That's it. It's really the slope formula. Okay, so then we just replace it for a general n instead of 1 and 2. So 1 and 2, and then we do the same thing for 3 and 2, and then 4 and 3. And so n is just the general case, right? So if this is our formula that we derived, x2 is equal to x1 minus f of x1 over f prime of x1. You could also say we could do the same steps for x3 and x2. Right, 2, 2, 2. So n, this is n plus 1, n, n, n.
Oh, there it says n equals 1.
Yeah. Okay. So do you want to try an example? Just one example?
So this would be useful.
Okay. The zeros, the x-intercepts of something that's not a quadratic, and you can't factor it.
Can we just use the quadratic formula?
Quadratic formula is only for quadratics.
Oh. Crazy.
Light bulb. Okay.
Why is it?
Okay, so there isn't. Okay, so here now I'm going to cheat because we're not actually going to have this on a test. And so graphing calculator, because of the store feature, makes it so much easier. If you have store, then it makes it easier. Okay? So here's Newton's, this is a cubic, right? And we want to see, okay, where one of the zeros. So if we want, okay, when is x cubed minus x minus 1? We don't really know, right? What? Thank you. Plus x plus 1. Okay, so our formula is this. This is Newton's formula. This is in the very end. Very end. Okay. So we're going to make a guess.
30.
Okay.
Is that too high? Is it way too high? Let's try 4.
Okay. Doesn't matter.
Wait, what if
So we want to start with what is x2. Okay. So we're going to make a guess. x1 is our guess.
What if we're too low with our guess?
It still will bring us back.
No, because it would go through.
No, it still would. It's because it's tangent. It's just going the other direction.
Yeah,
That's an ugly. So maybe it's here and you did it on this side. So this tangent right here it's still gonna give us it's still gonna bring us back over here. Yeah, it'll bring us back and then we'll get closer. Eventually it'll bring us there. Okay, work. Yes. Okay, so let's make our guess. We also need to know our derivative of our function. So what's our derivative of this function? 3x squared plus 1, because we're going to have to plug it in. Okay, now you said 4?
Yeah.
Sure, let's start 4. So our guess, x1 equals 4 is our guess. Okay, so what we're going to do is we're going to plug it in. So we have 4 minus f of 4 over f prime of 4 into our calculator. So this is why it's going to get easier, because we'll do this. So x, I'm storing 4 as x, okay, so that we can go, our formula is x minus, so on the numerator is f of 4. So the original equation was x cubed plus x minus 1 over, and then f prime of 4, the derivative was here, 3x squared plus 1. So we get our answer as 2.63. Okay, so this is going to become our new x. So now x3 is x2 minus f of x2 over f prime of x2. Okay, so what we can do with this guy now, go store x. This is my new x. This is why the graph, I love this thing. So nice, right? Second enter, go back to this guy, plug it in. What does that give me? 1.72.
Wait, it'll eventually just stop?
It'll start being the same thing every time.
Oh.
1.720, let's go there. So x4 would equal to, okay, so now we're going to store x. That's my new x. And then plug it into that guy again. 1.13. Notice the difference is getting smaller and smaller. Okay, store x. Again. Just keep going. So this is why, so x5 is 0.805. We started pretty far away, that's why. If we started with a smaller guess, would have been better. So store x. Okay, we're getting closer. 0.694. Okay, store x. Ooh, getting smaller difference. 0.682. Are we getting there? Yeah, so see where we're getting there? That's it. Okay, 0, because it says, well, you just keep going until it's the same thing every time. So we can keep going if we want. Yeah. So you're not, really the number's not changing. It depends on which program. If you're in engineering, you buy an engineering calculator. And engineering calculators will do derivatives and everything on your calculator for you.
What? No. Daryl not such a calculator? No, he uses like yeah, Daryl uses
Depend on the prof, depends on the school, but often scientific. And then your labs, often you're using computer programs. So you can really see, like, okay, what does a fourth dimension graph look like? Super cool. Okay, so did you want to do another one, or are we good to leave it there? Do you want to do one more? Are we good? So I'm not going to test you on this. If you want to do more practice, page 148 of your textbook. So you. Yeah, you would if you have to find the x-intercept, and you can't use a graphing calculator, right? That's it.
So
This is it.
so we are being tested on it.
So I will always give you things that are factorable, or you can use the quadratic formula.
So this is just for fun.
But if you can next year.
Yes.
Or for trying to
So this was just for funsies. Oh, I like this one. Okay. No, we're going to go through this guy. You can work on homework instead if you want to. Otherwise, I want to go through this guy. What? We're going to get it back. We still have lots of time. Okay, 25 minutes. Okay, so same page. All right, so this is really fun. Without a graphing calculator, and without technically, let's pretend your calculator doesn't have the fourth root function on your calculator. So, okay, so what? We're going to make that equal to x. So we're going to make a function. So first step is to do what to both sides? We want 0 equals. We want to turn this into 0 equals. Fourth it. Yeah. So raise both sides of the fourth, and then bring the 13 over. So we want to solve for when is this. So that's going to be our function. So that would be our function. So now we want, okay, we're going to make a guess. Let's make a logical guess. 2 to the 4. What's 2 to the 4? 16? Yeah, so let's start at 2. It's a nice number. So we're going to make x1 our guess of 2. And so our formula is x2 equals x1 minus f of x1 over f prime of x1. Helps knowing that formula. So then, now I'm going to store x is 2. So our formula is x minus, this would be x to the 4 minus 13 all over, what's the derivative going to be? 4x cubed. Oops. Okay, so then I get x2 is equal to 1.9. Oh, x3. Oh, no, that's x2. 90 actually? Yeah, 906. Okay, so then it's the set. So then x3 would be, so now I'd store that as my x and go through the same routines. x4. I just want you to see this so that one day when you get to university, they talk about Newton's method, like, oh, I've seen that before. Okay, we're getting pretty close, right? We're really, yeah. Did you plug, is it exactly it? 4 math 5, so 4th root of 13. Yeah, pretty close. We could have gone one more time, probably. Yeah, pretty cool, though. Okay, so that's Newton's method. That's only 4 in this, because our guess was really good, right? If you can give like a logical type guess, it's even better. All right, so that's it for today.